Hi again, AP Calc students. Time for lesson 3-2 on differentiability, a tough word to say, but one I think you will understand fairly readily. Again, we talked yesterday, the last lesson, about derivatives, and we once again saw the big definition for those. Now we want to look at some places where derivatives might not exist. Again, we always think of derivatives in terms of slope, so keep that in mind. So these are the four places where derivatives will not exist. Oftentimes we can identify them best just by looking at the graph, but we'll also talk about them in a little bit different fashion too, sometimes kind of algebraically. Here's my cat Puma to once again help me interfere with this lesson. Alright, first one's a corner, and you can kind of guess here why there might not be a derivative at x equals 0, because the slope coming in from this way will be different as the slope coming in from this way, and those slopes have to agree in order for that derivative to exist. So a classic example here is the absolute value function, but we'll see several other corners. Second one here is called a cusp. Cusp is kind of like a corner, except it's a little bit more curvy where those two lines meet. A good example here, x to the 2/3 power. A lot of times these rational exponents might produce a cusp. But as you can see, again, those slopes are going to be different as we approach 0. Here's a vertical tangent, our third place where derivatives might fail to exist. And if we really zoomed in on this area at x equals 0, we would see that there's the tangent to that point is basically vertical. And of course, when we're talking about slopes, there is no slope for a vertical line, so that's another case where derivatives won't exist. This one's a little bit more rare, but we'll see this especially when we get to second and third derivatives and all that kind of stuff down the line. Okay, and lastly, any type of discontinuity. Of course, here at x equals 0, we see a jump discontinuity, and when we have just a straight constant function here, of course, those slopes will be different coming in from each side. So, those are four places where derivatives cannot exist. Now, let's take a look at how we might find some derivatives on our calculator. You'll make use of these methods quite frequently. This first one maybe not so much. This is called the numerical derivative. And notice the definition of this, how this is calculated. This is called a symmetric difference quotient. When we first looked at derivatives and we looked at the definition, it was a little bit like this. We had x plus h, but then we had just minus the f of x, so the original function. What this does is examine that h value, or that distance away from the point, a little bit beyond the a value, greater than the a value, and less than the a value. This is a little bit easier for the calculator to figure out this derivative. So this is called the symmetric difference quotient. Where you'll find this on your calculator under the math menu, number 8 on my calculator here might be slightly different. It says n deriv, and if you select that, then you'll be able to put the function in there. Now your calculator might be slightly different. When I selected this, I actually got this derivative notation here. And for instance, I just put in x squared, which is a parabola. I wanted to see what the derivative was at x equals -3, and sure enough, it spit that right out at -6. Now, one thing to watch out for, what if I looked at the absolute value of x and I wanted to know that derivative of 0? Notice what the calculator gives you here. And I just like to pose the question to you, is that the correct answer? Why or why not? We'll see if somebody can tell me that in class tomorrow. So that's one way to find derivatives on a calculator. The way we'll probably mostly use our calculator to find derivatives or double check an answer that we have is under this calculate menu. So there you have to graph a function first. So I graphed y equals x squared. Go to that calculate menu, again that's second and trace on your calculator, and you'll see a lot of options that we've used before. But it's number 6 here that we want, dy over dx. That's one of the classic notations for derivatives. And when you select that, the graph comes up on your calculator. You'll actually be able to put in what specific x value you want to find the derivative of. So I put in -1 here. I selected that, and sure enough it spewed out that that derivative is -2. Again, remember that's the slope at that particular point. Those of you that remember from pre-calculus having to really grind out that derivative from the definition will appreciate and maybe be a little bit angry that you didn't know about this earlier, how to find the derivative at a point. So those are a couple of ways to find derivatives using your calculator. We'll be practicing on these quite a bit more in class. A couple of theorems here just to finish out. First one is one we'll kind of refer to quite a bit. Differentiability implies continuity. So the idea is if a function has a derivative at a particular point, then we are sure that the function must be continuous there. So if we know a derivative exists, then we can be sure that the function is continuous at that point. And I'd like to pose the question, is the converse of this theorem true? In other words, if I said if a function is continuous at a particular point, will it always have a derivative there? So I'll let you ponder that a bit. We'll talk about that in class somewhat. Now this intermediate value theorem, this theorem 2, this one's not quite as essential at this point, but basically it says if you have 2 points in an interval a and b, and we know that the function is differentiable, then the derivative takes on every value between those two derivatives. This is a little bit hard to understand. We just want to introduce it now. We'll be talking about this a little bit more detail in a later lesson. Anyway, thanks for listening, everybody. This is a fairly short lesson. We'll be working on this stuff in class tomorrow. Bye now.